Hello and welcome to this TA session for the course of Physics of Materials, which is an NPTEL course. It's taught by Professor Pratap Haridas from IIT-M, and I will be the TA for this course. My name is Mohammad Tehseen. I'm a PhD student at the Aerospace Engineering Department in the Indian Institute of Science, Bangalore. Um, as you might have seen in the introductory lectures of the course, what this course is about, this is about understanding why materials show different properties and how those properties are interrelated to each other and how sometimes these properties may differ from each other. So this course is intended mostly for UG students from uh, almost all backgrounds, and this is a very self-sustained course. What I mean by that is all the contents that will be covered in this course will be sufficient to understand the course itself. There will be no prerequisites or um, any background knowledge, any specific particular background knowledge that will be assumed. But yeah, uh, students from metallurgical department, material science, and as well as physics, UG students, they might find it more relevant to them. So let's begin this session. Um, so once actually the first TA session was conducted live on Saturday, uh, but unfortunately there were some issues with recording. So I am re-recording this session without participants, and so that any other participant for the course who has applied for register for the course, they may get back. I mean, they may access this lecture if needed. Okay. So the recording for this will be uploaded to YouTube, and the link will be provided. So let's begin. So I'll use my iPad to present my screen, and so that I can write some things. I hope my screen is visible. So we discussed a few things last time, but let me just start again from the beginning. Just trying to arrange the window size so that what I write is visible. Okay, we should be okay with this. Okay, so let's begin. So the name of this course is Physics of Materials. Okay, and the course instructor is Professor Pratap Haridas from who's a faculty at the Metallurgical Engineering Department at IIT-M. and I will be the TA for this course. We write my name here. It's Mohammed Tahseen, and I'm a PhD student at IISc. So, so let's begin by discussing what some motivational discussion about this course. What's the aim of this course? Who is it intended for? And what will be the outcomes of this course? So this course is about materials, and materials are found everywhere. We deal in our daily life experiences. We deal with a lot of different kinds of materials, and we from our common experience we can tell one material from the other by knowing their properties. Now, so for example, what I mean by that is if I have this pen in my hand, I know it's a solid, and if I try to apply some load, maybe it will resist that load, right? It will not deform easily. On the other hand, if I have some, let's say, some water bottle in my hand, and I just wiggle this, I can see the water slushing around inside the bottle. So, what I can like briefly say is that water is not as resistant to loads as a pencil. Okay, so this is just a basic example. The point is that we are surrounded by different materials, and all the properties of those materials are different from one another. And although we know from our common experience, we understand intuitively how those properties, why like how different materials have different properties. But the goal of this course is to understand where those properties actually arise from within the material, and what is it that makes one particular material behave one way and the other material behave the other way. Okay, so let me just drag this window. Probably I cannot. Okay, so that will be the goal of this course, to understand basically the properties of material. And so I just talked about, in the example I just discussed, the water and pencil example. I only discussed one particular property, which some of you may recognize that I only talked about the mechanical properties. I did not discuss about other differences, other ways in which a pencil and a water differ from each other, or other ways in which a pencil and water may be similar to each other. So, to formally understand this, we that's the purpose of this course, to be able to differentiate or differentiate between two materials, or to argue if they are similar, in what manners they are similar, and in what manners they are different. Okay, so this course, physics of materials, it could be useful to so who is this course intended for, right? So the question that I discussed briefly now was, why study the physics of materials, right? Why study the physics of materials? Okay, and we argued that we study the physics of materials to understand their behavior, to understand rather not just the behavior but the origin of behavior. Okay, origin of properties, and we will look at this word properties in more detail, to understand the properties of materials. Okay, and what else can we remark here? We can say that what does this understanding allow us to do? Okay, uh, so it allows us to differentiate materials based on their properties. And we can again ask, why do we need to differentiate the materials based on their properties? Okay, and it's the answer is quite obvious. We, if we are trying to design a particular application, we so any kind of application, innovation, machinery, technology requires materials, and it's important for us to use the correct material as required by that application or that property. For example, I cannot use water for to carry loads. Yeah, right. I can use a, for example, a piece of wood or a steel bar to as a truss element. I cannot derive the exact same function for water. Right? And similarly, if my application requires, let's say, some kind of an hydraulic actuator, right, which works on the principle of this hydraulic action. I cannot use that same. I cannot use a structural member to derive that function. So it's important to use an appropriate material for the appropriate function that we are trying to design an equipment for. So that's why we need to differentiate between materials. We need to understand the properties of materials so that we can design properly as engineers or as scientists. So that's one motivation. Now, so who is this course intended for? Right? Or a better way to ask that question would be, uh, like it's a sub part of the uh, first question that we asked. We can ask, who benefits from, or why is it necessary? Uh, let's write it this way: where is the understanding of physics of materials applicable? Okay, where is this understanding of physics of materials applicable? So this is uh, so we can basically, let me just highlight two headings where the use of this physics of materials is like mostly found or mostly required. So first would be industry or technology, or let's say manufacturing, these kinds of industries. Okay, let's say someone is a, I think I discussed this example last time as well. For example, let's say someone is working as an engineer at some, let's say at GE Aerospace, and they have to uh, design a blade for their turbine. Now, what would be their expectations of the material or of the blade that they are trying to design? So their their expectation would be that first of all, the blade should have a long fatigue life. Now, what's that supposed to mean? For example, say we have a rotor here, okay, and on this rotor there are some blades mounted. Let's say this is a rotor and these are the blades. Now these blades, they are subjected to loads of various kinds. Okay, let's say first kind of load that is applicable to these blades is the load from let's say load from load due to the combustion gases, right? So this would be one kind of a load that's applicable on these blades, right? Basically, inside the engine, the fuel burns and it produces an exhaust. The gases produced from this exhaust, they move at very large speeds. They carry very high kinetic energy as well as pressure energy. So inside the rotor, when those gases impinge onto the blades, they transmit their energy to these blades, and there are various kinds of conversion of energy that happen there, and ultimately the blade rotates. But during this process, the gases that come out of this exhaust, I mean from the combustion chamber, they carry a very high velocity, okay, and due to which uh, uh, so that gets converted in these blades. Now that conversion, often during that conversion there's a very high forcing function on these blades, and these loads are repetitive in nature. Okay, so in every cycle, in every single rpm, in every single turn of this blade rotation, 2 pi rotation of this rotor, that uh, uh, that that this forcing function could be a multiple of that the number of rotations it does in every minute. So that would be a way to calculate the frequency of this forcing function, right? How many times in a particular cycle does the same blade uh, uh, come in this field of combustion gases. So this gives rise to what's called high cycle fatigue. Okay, high cycle fatigue inside the turbine engine, and this is one of the major causes of failure of these blades, which is the high cycle fatigue. So this is an example of one kind of load that is the load that is faced by or carried by these blades. Now there could be some other uh, forces as well that are carried by these blades, and an example of that would be, let's say, uh, dynamic loads, dynamic loads due to imbalance. Okay, So what is the origin of these loads? Now, in any machinery you design, it is practically impossible to make the center of gravity coincide with the geometric center. Okay, like theoretically we can always show, if this is the, let's say with red I am showing the geometric center, and with green I am showing the center of mass, which is actually I mean for the whole assembly. Okay, now it's in practice it's never possible to create such a perfectly homogeneous material that these two centers would coincide. So this gives rise to some offset, which we call eccentricity. Okay, it's called eccentricity. Now, due to this eccentricity, there are again unbalanced loads, right? Because now there's a moment arm which is equal to this eccentricity, this distance between the two points, and in every rotation, there's an unbalanced force which is uh, is carried by the whole assembly and blades in particular. And so this would be one more uh, cause or one more source of forcing on the blades. Now there could be one more which can be readily seen, which is centrifugal force. Okay, centrifugal force due to their own weight, due to the weight of blades. Right, because these carry a weight m, a mass m, and so any given mass, if it's rotating with an angular velocity of omega, then the centrifugal force on that particle is m omega square r. So we can, if even if we consider in a simplistic assumption, we consider the blades to be point masses, then there will be a force applicable on them. And in general, because blade is not a point mass, it's distributed along the radial lines, this mass, so there will be uneven forces. There will be a distribution of these centrifugal forces along the length of height of the blade, which is also called the span. So this is one more reason, and there could be other forces as well. Okay, uh, so we just saw an example of three kinds of forces that are applicable to blades. One is the aerodynamic forces because of the hot combustion gases, and second is the dynamic loads due to imbalance. Now there are also thermal gradients produced by these combustion gases, right? So because these gases are quite hot, they are at very high temperature, and when they strike the material, part of the material is heated instantly, while some other part of the blade near the root, that could be uh, lower in temperature, right? Say this part, this could be at a lower temperature, while as these parts could be exposed to high temperature. Now that also sets up a thermal gradient inside the material, due to which there are again thermal strains and stresses. So it's a very complex kind of situation. And if we have to design a blade which could withstand all these forces, okay, then we need we need to know how the material of the blade responds to these different kind of loading scenarios, right? Without the knowledge of the material, we can never design uh, this blade. So Yeah, so that is the, and all of these forces, they could be, uh, they could give rise to either high cycle fatigue or low cycle fatigue as well, right? So for example, say the failures which occur at below 10,000 cycles, those are mainly due to the low cycle fatigue, and the high cycle fatigue failures, they occur at uh, uh, higher number of cycles. So there are different forces which are responsible for these two different kinds of failures, and it may be required to uh, improve or tailor the material behavior based on the experience, failure experience. We may need to increase one or both of these limits for the material, and this can only happen if we know where the properties of these materials, where the properties of this material to have a resistance against these loads come from. Okay, so that's why the knowledge of physics of the materials is important in this case. So another example, so this was more of an industrial problem, which uh, which it was to motivate that the people from industry working on these kind of applied properties, applied cases, right, or problems which need immediate solution. The physics of knowledge, the knowledge of physics is important to them in order to be able to design and redesign their components. So for similarly for people in more of a, let's say, an academics, okay, from academic research point of view. So the knowledge of physics of materials is important here as well, and it's this knowledge which allows us to uh, do different things or achieve different goals. So one common example, I'll cite one example. Say someone wants, uh, let's say, let's talk about material discovery. Okay, material discovery. So what is material discovery? So the name is self-explanatory. Material discovery is discovering a new material. Now, how does one go about discovering a new material? Is it by luck, by chance? And it could be, for example, there are several materials that we know of that have been developed accidentally, right? And so those accidents are, they cannot be planned, they cannot be one cannot hope for to have an accident, such a happy accident in their life. That's not how things work. If such an incident happens, it's a happy event, but it's not a procedure, it's not something that we can train ourselves for. Okay, so there are more robust techniques that involve quite a bit of understanding of how materials behave, so in order to improve their functionality. So one common way of, let's say, achieving this material discovery uh, objective, that can be like one of the ways that I know of. I'm sharing it from my own knowledge. It is by tuning the composition of materials. Okay, so by compositional tuning, by compositional tuning, right? So what does this mean? So say we have an alloy in which there are some three metals like A, B, and C. So these are three metals, and let's say their proportions are x, y, and this would be 100 minus x minus y. So these are the compositions where x could be either atomic percent or weight percent, doesn't matter. So let's say we want to optimize this material system to enhance a particular property, and this could be any property. It could be mechanical property or some thermal property or any other property. So how do we do this? Okay, so how many compositions will there be? That's one question that we can ask, right? How many compositions are there possible? And like in theory, there are infinite possibilities, right? But even if we set because x and y can vary from whatever 0 to 100, so even if we assume some kind of a compositional like a step. So if we don't talk of continuous variation, but we fix some unit, some incremental unit by which we incremental or decremental unit by which we change the composition, let's say by 0.1 units. So we are giving now it a discrete step, discrete incremental or decremental step. Even then there could be a lot of possibilities, uh, possibly thousands of possibilities there. So how do we go about finding, let's say there is some property eta. This could be anything. So how do we optimize, let's say we want to increase the value of eta as high as possible. So how do we design our system to find a composition where this property eta maximizes? Now again, one a very non-technical way would be to manufacture all the compositions, right, and then see one by one where this property eta maximizes. But this would involve probably years of effort, and finally the property of eta, like we really have to ask ourselves the question, is it worth the time and effort and the resources to uh, to use this procedure for finding a particular or meeting a particular objective, or is there any better technique that we can use to achieve the same objective or to guide us uh, towards a favorable zone in this compositional space? So that is one of the things where the knowledge of physics of materials is handy. uh, for example, uh, one way to think about this is, if I is the so is replacing by is replacing A by B, does it have the same effect as if we replace B by A? Okay, so increasing x or x for y, replacing x for y or y for x, does it have the same effect? And that knowledge comes from by knowing what A and B are, and how A and B uh, behave in this material system. What are their roles, and can we substitute one for another, or if we do, what would be the effects? So this is a very interdisciplinary kind of problem where we are interested in uh, uh, basically exploring the whole compositional regime. But here also the knowledge of physics of materials is really useful to us in terms of saving of resources and time, and of course manpower. So this is one example where academic research could could benefit or does benefit from the knowledge of physics of materials. Okay, so let me just give one more example, probably a final example for the motivating the subject. And this example is of a shape memory alloy. Shape memory alloys. Now, many of you might be familiar with shape memory alloys. So these are the materials which somehow remember their shape, which store their shape, and hence the word memory. So what are these alloys? Okay, so I'll write one famous shape memory alloy, which is probably the most famous shape memory alloy and most successful as well, which is called nitinol. And what is nitinol? It's nickel and titanium. It's an alloy of these two metals, and the composition is almost equiatomic. Okay, and this alloy displays a behavior that is entirely different from the behavior of nickel or from the behavior of titanium. It gives rise to a very different property, which is the property of shape memory effect. So what is the shape memory effect? So let's say I have a piece of wire here. Okay, let's say this is I will call it a conventional wire. Conventional wire. Wire, by conventional I mean a wire made of some conventional materials, say steel. Okay, let's say it's steel. And let me also assume that the length of this wire is some L original. Okay, LO. That is the length of this wire. Now what I do is, if I apply some force on this wire, okay, let's say I apply some P1, P2. These are the forces that I'm applying to this wire. So what do I expect to happen? Okay, probably the wire will bend at these places where I apply a load, right? It's simply, for example, if this is some kind of a wire and I am just applying a load here in the middle, it will just bend. Okay, this is the kind of experiment that we are doing here. So let me, in a schematic way, let me redraw the deformed configuration. So it would be something like this. So at the points of load, I am assuming that it will deform. Okay, it will bend basically. And length would be, it's not uh, necessary that the length remains constant. Let me call it LD, some deformed length. Okay, so this is what will happen. This will be the deformed shape. Now what I'll do is, so yeah, so I have deformed this material, and after that what I do is I heat this material. So let's mark the steps clearly here. This was applying load, and the next step what I am going to do is I am going to apply heat. I am going to heat this wire. Okay, and let me bring it here so that I can redraw this wire. So what do we expect to happen if we heat this wire? Almost nothing, right? it will be mostly the same. Maybe if we heat it too much, it will get hot and probably it will change color. And there might be a still, you might argue that because we are heating it, it will expand because metals generally expand on heating. So let me say that it changes its length from LD to LR, sorry, LH, where LH is now the heated length. So that is at most what will happen, right? We don't expect anything else to happen. But if we do the same experiment on a shape memory alloy, okay, let's say I take the same thing and now instead of a conventional material I have, let me use green color here, I have a shape memory alloy. This is now a shape memory. Let's say this nitinol wire, let's make it specific. Let's say this wire is nitinol wire, okay, and I take the exact same situation again. I start with the length LO, original length. I apply the same loads P1 and P2. Now let's say I get to some length LD, which is the deformed length, and the shape is also changing. It's a deformed shape, and deformed shape is highlighted here in this one. And then I apply heat, but in this case, for this particular material, what happens is when you heat it up, okay, it will directly go to this configuration, the original configuration, right? So it is as if the material remembered its original shape before the deformation, and hence the name shape memory effect. Shape memory, yeah, shape memory effect. So what happens is, what different is happening here? Why does one material, we take for example, we took the steel wire, we heated it and nothing happened, but then we took a shape memory wire and we did the exact same experiment with the exact same values of load and length, but something else happened. So clearly, if you ask, for example, a common person, a common man, without the who doesn't have the knowledge of materials, the knowledge of physics of materials, how would he argue about this, right? He would be amazed because he will not be able to resolve uh, this uh, experiment. So something is different about, because if you take a steel wire and if you take an ethanol wire, maybe on a visual level, from visual inspection, they might both appear same, more or less. Okay, so it's very hard to differentiate or even observe. Uh, Not observe, we can observe what's happening, but rationally we cannot argue what is happening inside, what's happening, why is there a distinction between these two materials. So that's why we need the physics of materials to come in here and help us with the explanation of these effects. So since I'm on this topic, let me say a few more words about shape memory alloys. So yeah, so this is one of the effects that this wire, nitinol wire, shows. Okay, and this is not the only effect it shows. So if you notice here, we had to apply some heat. So of course, one of the questions that one could ask here is, apply this heat, why are we applying this heat? Okay, and what is the ambient temperature at which we are doing this experiment? And do we always need to heat? And what if the ambient temperature is already high? Do we still need to heat in that case? and that's what causes the difference. Okay, so normally if this material, okay, if this material is kept at a lower temperature, okay, so there is some critical temperature, let's call that transformation temperature. Okay, transformation temperature, transformation temperature, and it's fixed for a particular shape memory material. Let's say for nitinol, this transformation temperature, I'll represent it by Tc, and let's say it's fixed. Okay, and if we are conducting this whole experiment below this transformation temperature, in that case, what I discussed above, this is what happens. Okay, if we take below the transformation, so this whole experiment, it is for T less than Tc. Okay, now what if T is greater than Tc? In this case, what will happen if T is greater than Tc? So some of you may know it, some of you may think and arrive at this conclusion that we will not need this step at all. So this step goes away. Okay, so what happens then? What will happen is, as long as you are applying this load P1 and P2, it will remain in this state, right? Because of the forces, because the forces hold it there. This is the equilibrium configuration under these forces. But as soon as you release these loads, okay, the material will go back automatically to its initial state, because now the ambient temperature is doing the job of heating itself. Okay, so let me call it goes back to reference state. Okay, and this phenomena is called superelasticity. Why superelasticity? Because the amounts, so elasticity is basically the property of a material to come back to its original shape when we release the loads of, that we had applied to it. So we apply some loads, the material deforms, and when we release those loads, if the material comes back to its original configuration, we say that the material is elastic, and this is the property of elasticity. And the most famous example probably is rubber, that is used to make this point. So why super elasticity, right? Because it is because in some limit every material shows some elastic behavior. So even if we talk about a steel wire and we are applying some loads to it, under some some uh, uh, window for this load, some limit within that's called actually the elastic limit. So if the loads are constrained within a particular limit, the elastic limit, the material will regain its original shape when we release the loads. That happens usually for all materials, but the amount of that strain that can be recovered is very low. And in fact, in these shape memory alloys, you can recover up to 10 to 15 times more, 10 to 15 times more strain can be recovered. as compared to elastic limit of solids. Okay, elastic limit of conventional materials. And hence the name superelasticity. And uh, the um, the effect of thermal dilation or thermal expansion, thermal contraction, those effects are very negligible as compared to the strains we are talking about. So we usually don't talk about them at all in while dealing with these materials. Okay, because the order of magnitude is much larger. And the previous case, this is called the shape memory effect, where we have to use an external stimulus, which is heat in this case, to arrive at the original configuration. So why I like this example is because it tells us something very interesting, right? The same material performs two different functions, and based on, so we can have a lot of applications from these two effects. For example, from using the shape memory effect, we can design switches, actuators, thermostats, right? Which respond to heat basically. Okay, so if it senses heat in its environment, then it can actuate itself. It can change its shape and serve the function of a switch or an actuator, and both actually, both at once. So it can sense, so it is the sensor and the actuator itself, the material. We don't need to have a separate sensor and then some actuation mechanism and then another mechanism which does the job. All these things are integrated inside the material, so it's an intelligent material, and it comes under the category of materials what we call smart materials. So that is one effect. Now we can also use this super elasticity, and it has a wide range of applications ranging from uh, wheels of you know, so if we talk about these extraplanetary missions that are conducted by NASA, uh, let's say there's a rover that has to be sent to the surface of Moon or Mars. Now the temperatures at those extraterrestrial places, they might they are actually not favorable for rubber to be uh, a valid material there. So at those temperatures, surface temperatures, the material, the rubber suffers from embrittlement, so it will basically break like a chalk. So we can't use a pneumatic tire there as we use here on the surface of Earth. So we have to search for alternatives. And actually using this shape memory alloy and using the property of superelasticity, NASA has designed a wheel which they call the smart tire or SMA tire, which can basically deform more than a rubber, or at least as much as the rubber tire does. And then as it rolls over the obstacles, let's say there is some rock and the tire has to go over this rock. Okay, it can deform, it can take up the deformation. The tire is made of this SMA wire mesh. These wires are meshed together to create this tire structure. Okay, and as the wheel rolls over, it deforms here while it's over the obstacle, and as it passes, it releases all that deformation in the without causing any permanent damage to the material, because this is all the elastic in the elastic limit. So there are numerous applications based on these two effects. So how did we like, what's the story of shape memory alloys? Did we always know about them, or uh, like how did it happen? What's the story of this material? Okay, I'll come to that, but I'll just reiterate the point I was making, that the same material is performing two different functions, right, at different temperatures. So it is as if it's showing different property at based on the temperature at which we are using it. And that is actually one of the goals. Like later in this course we will see that material behavior is a function of its temperature, pressure, and all that. Okay. So yeah, so let me now tell you briefly about the story of this shape memory. So today's lecture is mostly a motivational lecture or introduction to this subject, just to gain some insight into what this course is about and what it will teach us. Uh, from next session, which is the second session, we will start looking at the some of the course content, and eventually we will discuss other things as well. So what's the story of SMAs? Right? So there's a there's an organization in United States which is called Naval Ordnance Ordnance Laboratory. Okay, and the story of shape memory alloys begins from here, and it was around 1960s, 1959 to be precise. So there was one scientist, I think his name was Bueller, and he was assigned. So this Naval Ordnance Laboratory, uh, it works in defense sector. So many of its projects are defense related, and he was working on one particular material. He was working on titanium, actually an alloy of titanium and nickel, and again he was interested in optimizing its fatigue strength. So he was trying out different compositions, and once in a meeting. So this is all, I mean, the details might be here and there. This is one version that I have heard, but in one meeting, it said that while he was presenting his this material to his colleagues, uh, he had a wire sample of that material that he was demonstrating, and he demonstrated some behavior of that material, and he passed it around. And the same sample of the wire, he passed it around the, let's say there was a table, and all the people were sitting there, and as he passed around the material, people took the wire sample in their hand, and they might have twisted it, bent it, or just stretched it, and it passed from one person to another. And there was one person in the on the table who used to smoke. He was a pipe smoker. So he took his lighter and he started heating this wire. And to everyone's surprise, the wire flattened out. Okay, it regained its original shape, which is the straight shape. So this was a this is how SMAs were discovered, and everyone was shocked about seeing this behavior. So uh, then everyone started asking the question, okay, what's happening inside this material? And finally it was, I mean, then people got interested, people did microscopy and all that, and finally they found out that this uh, the whole concept of the shape memory effect and superelasticity, these arise from phase transitions. Okay, phase transitions inside the material. So what is a phase transition? Phase transition simply means that one crystal structure, so this is a metal, it has some crystal structure associated with it, and when we change its temperature at the transformation temperature, this crystal structure goes to another, it's a different crystal structure. Okay, on heating. And this is not sufficient for this phenomenon to occur. This process is actually reversible. Okay, this is reversible. So when you cool it at the same transformation temperature, it returns to its original crystal structure. Okay, so let's say this is heating and cooling, and this is T less than Tc, and this is T greater than Tc. Okay, so in this material we see that the crystal structure is a function of temperature. As we change the temperature, the crystal structure also changes, and that gives rise to the fascinating properties in this material. So now this is, I mean, if we look at it, this is the physics part of it. Okay, what those people observed in that meeting, that was serendipity. Okay, that was an accidental discovery. But if people had stopped at that level, no one would have asked the question, okay, why does this material show the behavior it does? And it's only when we ask such questions, that's how we explore the physics of materials. And once we explore the physics of materials, we can put them into use for different applications. As we see in the world of today, shape memory alloys have vastly progressed in various fields, ranging from biomedical to robotics to aerospace industry. And so this is how materials are born. This is how science progresses, right? By asking questions. So that was the story of shape memory alloys. And by the way, the name nitinol comes from this. It's an acronym, right? NITI is the nickel and titanium. Then NOL comes from this Naval Ordnance Laboratory, the initials of this place. Okay, so yeah, so let's move on to some next line of discussion, which is about properties of materials. So what are properties of materials? Okay, so these are the characteristics with which we identify a particular material. For example, this pencil can take a load while water cannot take the load, right? Or all kinds of loads. So that's one mechanical distinction between these two materials. And uh, so it's not the only way. I think I said this in the beginning of the lecture, that it's not the only way or the only similarity or dissimilarity between these two materials. There could be others as well. So these characteristics shown by the material, these are called properties of materials. Okay, and it's because of these properties that we are able to classify materials. So when we say, for example, if we ask the question, uh, what kind of materials are good conductors of heat? Okay, so the question in itself is it poses uh, yeah, a classification, right? It asks for a classification based on some property. And these are the, like, when we classify materials according to their properties, then we that's how we create databases, and that's how we know later if we have to go and check, design a particular application, and we want to find what's the proper material or what's the most suitable material for that application. We ask ourselves the question, okay, if this is my material, what is it expected to do? What am I expecting from this material? What are the electrical properties that I want from my material? What are the mechanical properties I want from my material? Right? So we collect all this information, and then we go to the database. We see what are the materials that satisfy the electrical requirement that I have. What are the materials that satisfy the mechanical requirement I have? And similarly for other kinds of properties as well. And then we find the best material. Maybe if there's a common material which satisfies all of the requirements that we want. That's how we select a material for our application. So that's why properties, to explore the properties, to measure, to quantify them, these are all the different aspects of discussing the properties of materials. Okay, so mainly in a broad way, we can a material can have different kinds of properties. Okay, so one of them is mechanical properties. Okay, mechanical properties. Now, what are mechanical properties? Mechanical properties, these are the properties that have to do with the mechanics of objects or material, right? So, for example, now what is mechanics? Mechanics is the study of how things move, how things displace, right, or how things deform. These are all different concepts of mechanics: deformation, displacement, motion. So to study these things, these aspects, this comes under the framework of exploring the mechanical properties of a material. So the basic example, again, very simple example: if I apply a force on this pen, what will happen to this pen? Okay. So that study in itself would constitute the mechanical properties. Now let's complicate it a little bit. Okay, so this is a material, and so the question is, what are the different ways in which I can apply load to this material? Right? So I can either hold it at one end. Let's say I am holding it at this right end, uh, which is your left, I think. So, and I am applying load at this end along the axis of this pencil. Okay, so that would be one way to load it. Now again, while holding this, if I on the other end I apply a transverse load, that would be another way to load this. Or say I hold it and I just try to bend this. I just try to bend this like this, or I just hold it in my two hands, and using both my hands I am trying to bend this. That would be one more way to load it. Or I am holding this at one end and I am trying to twist it, right? That would be one more way. So these are different ways in which I can explore the mechanical properties of this material. And it's not at all necessary that uh, the response of the material in these different scenarios, different loading conditions will be similar. It's very much possible that in for example, a basic, again, let's go to the basic examples. Let's say I have something like this. Okay, it's an earphone wire. Now see what happens. Let's say this is one end, I am holding it at one end, and I am pulling on the other end, right? I'm pulling on the other end. In that case, this earphone becomes stout, right? But what if I start compressing it slowly? You see, it does not take any compression. So it can sustain itself in tension, it can sustain a tension, but it does not sustain a compression, right? And furthermore, even with the slightest push, I can bend it, and it cannot even hold its own weight, right? It just deforms under its own weight. Now, on the other hand, a pencil, it can take all kinds of loads, right? Tension, compression, bending, it resists bending. So so this is about resistance, right? What kinds of loads does it resist and by how much? So this is what constitutes the mechanical properties of any material. These kinds of studies. Okay. So next is, we will look at a little bit more detail of mechanical properties, but let's first list all the different kinds of properties that are relevant to the discussion on materials. So second, I would say thermal properties. Thermal properties. Now, what are thermal properties? Okay. Now, thermal properties, as the name suggests, this has to do with interaction of material with temperature, with heat. Okay. So, what kind of things do we expect to happen when we heat a material or when we cool a material? So, the basic thing that which we discussed briefly earlier is the thermal expansion, right? If I heat a material, it will expand. That's the basic property of of thermal expansion. For example, if I take a rod again of this shape, this is a rod, and if I heat it, it will change its length. Okay, and okay, when I say change its length, it can also have two meanings. Does it expand or does it contract? Or is it possible for a material to, because intuitively it feels more comforting that if we heat a material that it will expand, but it's slightly more non-obvious to think of a material which would contract on heating, right? But there are such materials as well. So then the question is, why does one material behave in one way uh, when we heat it, and the other material behaves in another way? So that is that question. The answer to that question, again, it involves going into the uh, depth, more depth than the apparent uh, inspections and visual inspections. It involves to go into the discussion of what's happening inside these materials when we heat or cool them. So that is one kind of a thermal property. Now, what other properties could there be associated with the temperature? We can take the example of water again. So let's say, yeah, boiling points. So if I heat water, it's a very well known fact that water boils at 100 degrees. And what about milk? What temperature does milk boil at? And if the boiling temperature is different, why is it different for milk and water? Or let's not even go to milk. Let's add some salt to water, or let's add sugar to water. What happens to the boiling point then, right? And the question of, can we add something to water to increase its boiling point, and can we add something different to water to decrease its boiling point? So these are to for example, if we add milk to water, will the boiling point go up or down? And if we add sugar to water or salt to water, what will happen to its boiling point? Are these two effects the same, or will they change the boiling point in a different way? So you may have had a flavor of this discussion in the high school chemistry, where we discuss Raoult's law and uh, this one more Henry's law and Raoult's law. So that's what governs what will happen to the boiling points, and ultimately it's also a thermal property of material. Now let's explore one more thing. What about if we, yeah, so let's say I have two different metals. Okay, let's say a metal A and metal. Let's say we have copper and we have uh, aluminum. Okay, copper and aluminum. Let's say we have these two. These are the materials that we usually encounter in our everyday lives. So we have a kind of a feel for them, how they behave. So what happens if let's say I give 10 joules of heat to uh, uh, both of these. Let's say I have some specimen, okay, one block of cube. So I have two blocks of two cubes, similar, identical, and then one is made of uh, aluminum and one is made of copper. And let's say I give 10 joules of heat to each of these cubes. Now the question I'm asking is, which one will show a greater change in temperature? Which one will the temperature of which of these two will be higher at the end of this experiment, right? So I'm giving the same amount of energy to both of these, and I'm asking the question, will the temperature, let's say initially both of them were at 25 degrees Celsius. Now after giving a 10 joule of energy to both of these blocks, what will be the final temperature of these two blocks? Will it be the same or will it be different? If it is the same, then why it is same, and if it's different, then why is it different? Okay, and it's here uh, that the concept of specific heats comes in, or the heat capacity of solids. Okay, so that's also a thermal property, and similarly we have lots of other thermal properties as well, right? So next in the list we can discuss electrical properties, right? Now what are electrical properties? Electrical properties, these have to mostly to do with the how charges flow inside materials, right? For example, we may know very well from our knowledge that metals are good conductors of electricity, right? So, and let's say wood is not a good conductor of electricity. Okay. So the question is, okay, if I take now the same one block of wood and one block of copper, identical in shape and size, and I connect them to uh, let's say I break up a circuit. I take some electrical wire, break it up, and then connect it to the two ends of the uh, block. In each case, first for the copper block, then for the wood block of wood. And let's say the this wire is connected to one end of a bulb, light bulb, and the other terminal. We also have another terminal that directly connects to the bulb. Then we ask the question, will the bulb glow in the first case or in the second case? Right? So we may know from common experience that it will not glow if we connect the circuit through a block of wood, right? And this is the reason. The reason is because wood is not a good conductor of electricity. Then the question becomes, what makes an object or a material good or bad conductor of electricity, right? So that is the question. That's an electrical property that we might be interested in. So are there other electrical properties? What other electrical properties are there? So yeah, so that is basically the idea is the same, but we can again ask the question, to what degree. So let's say we have now a block of wood and we have a ball of wood, okay, and we do the same experiment with wood and then ball of wool. So again we may know from our basic experience that in both the cases the bulb will not glow, because both of these substances, the wood as well as the wool, but the material is a bad conductor of electricity. It does not conduct electricity. But the question is, if we keep on increasing the current, which one of these materials will give in first, right? So that could be some measure of a strength of that material to resist the flow of electricity, right? And even air in itself may have that kind of a threshold. Okay, so even air could start conducting electricity at some situation, or does it? Right? So these are the kind of properties that are associated with, or that we study under electrical properties. And now, okay, so I want to make one more point, but let me first write all some more properties. Okay, so we could have optical properties as well. So what are optical properties? And optical properties have to do with the interaction of material with light, and it's a very not yeah, so I mean in general with electromagnetic radiation, but when we say optical we are talking about a particular range of frequencies, particular bandwidth of the spectrum of the electromagnetic radiation, which falls under this visible light, and that is around, let's say, 400 to 750 nanometer. Okay, around this range. So how does a material respond to uh, the electromagnetic radiation in this range? That is what determines the optical properties of a material. So what are different optical properties that we usually encounter? So a very basic optical property that we often see is some objects are uh, transparent, while others are not, right? For example, if we look at water again, so water so this all also makes the point that in how many situations can we discuss water? We can discuss each of these properties for each of the materials, right? So is water transparent or is it opaque? Now, water is clearly transparent, but are there other liquids which are opaque? What about milk? Milk is opaque, right? uh, so what is it about a material that makes it transparent or that makes it opaque? It's a very simple question, but the answer is not so simple. It has to do with uh, how the constituents of that material interact with electromagnetic radiation, and that too in particular this range that I mentioned, right? So that could be one of the optical properties. Now like even in the circumstances, let's talk about these opaque sorry about the transparent systems. So let's take two different transparent systems, glass and water. Both of these are transparent, right? So we can see through them. Now the question is, do they have the same magnitude of, so whatever interaction they are having with light, is the magnitude of that same for both of these materials? Or is the so if we find some quantitative measure, let's say a refractive index, right? You may have heard of it from high school physics. So is it same for these two materials, or is it different? So even two transparent systems are not the same, okay, or they don't have to be the same. And why is it that two different materials have different refractive indices? And once we understand that the way this interaction happens, or the way this definition of refractive index comes from, we can design, and we can basically have the applications like fiber optics, which relies completely on this understanding of refractive index. And that's what makes possible the communication today. Okay, I'm recording this lecture and I will upload it to YouTube and you will access it. All of that is possible because of the fiber optics. That's how our internet works basically, right? At the core of it, that's how I am able to store this data online and you can retrieve it later. So that's one of the, or two of the optical properties that are relevant to the discussion of materials. Now, yeah. Now, other properties, there are more optical properties. For example, and there are some quantities like transmittance or transmittivity, then reflectivity. Uh, it again has to do with how much of energy is allowed to pass through a material, or how much of energy is reflecting from the surface of a material. And based on these, if we design a material which reflects most of its energy, then we can use that, for example, for some kind of insulating application, because it does not allow the radiation to pass through. And similarly, we can have applications like so there's actually one nice application that often comes up in the NCRT text in our high schools, which is the application of a solar cooker, right? A solar cooker. So it has a bright mirror which reflects the sunlight, and then uh, it has a chamber which is basically uh, black. Okay, so so on one end it's focusing the entire energy, that mirror is reflecting all of the energy which is getting trapped into something, right? So it utilizes, in a way, it utilizes both of these properties, right? to, and it's a very nice application. So these are the optical properties, and then again we can also expand it into how how optics, or how this optical range of electromagnetic spectrum, how it interacts with geometry of materials. And then we can have applications like lenses, which also have a very wide application, and ranging from, let's say, our the eyeglasses that we wear to lot of biomedical applications, microscopy, and then space exploration, telescopes, binoculars, and whatnot, right? So this all falls under the domain of exploring the optical properties of materials. And we can also have magnetic properties. Okay, Now, what are magnetic properties? Everyone knows what a magnet is, and people are usually fascinated by magnets, and they should be. So, so what is a magnet, right? Probably it's a very simple question to ask, and again, the answer is not so simple. So, a magnet, basically, again, how the discovery of magnets and all that, that's a story in itself. But a common experiment or a starting point of this discussion can be the observation that some some materials are attracted to a magnet while others are not. And even these don't have to be very different classes of materials. Both of these can be metals. Some metals are attracted to magnets and some are not. For example, if you take a piece of iron, it will be attracted by a magnet, but if you take aluminum, it will not be attracted by a magnet, right? So what is the difference between the two materials that causes this difference? So this discussion could fall under the discussion of magnetic properties of materials. And then even, okay, let's say we have two magnets. We have two magnetic materials, and by magnetic materials I mean the ones which now interact with this magnetic field. Are all the materials are all such materials the same? Are all the magnetic materials same, or are there further classes and divisions, right? And there we could discuss, for example, hard magnets and soft magnets. There are hard magnets, but are soft magnets. And we can also understand why there is such a difference of behavior, right? What happens at the uh, micro scale, micro structural level inside these materials that causes the two classes of materials to respond differently to magnetic fields. Or we could also have materials that get repelled by magnetic fields, right? Diamagnets, the diamagnetic behavior. So again, yeah, the question is what causes all of this, and what happens inside the materials actually that brings about these properties. And we can go on, we can list some more classes of properties as well, but these are some of the mostly discussed properties of materials. Okay. And now an important point that I want to make. An important point that I want to make is that these properties could be interrelated. It's not necessary that these properties are distinct, unrelated, and independent, right? For example, we discussed copper, right? Copper is a good conductor of electricity, but it is also a good conductor of heat, right? So, is there a correlation between these properties? Every material that's a good conductor of electricity, does it necessarily have to be good conductor of heat as well, right? Or uh, let's look at the other way. Let's take an interaction between, for example, so the case of shape memory alloys that we discussed earlier, right? So there we see a coupling between mechanical properties and thermal properties, right? We saw that if we deform the material, so that deformation in itself is a mechanical process. We are applying some loads that's causing some deformation, and then we are heating this material, and so there are two different fields applying that we apply on the material, right? First is the mechanical field of loads, and second is the thermal field of heat. So we see that these properties interact with each other as well, right? To give rise to some functionality. or the other case where we heat a material and it expands or contracts, right? That is the inverse process. We basically the thermal actuation causes the material to have some mechanical response, right? And we so one more reason, one more observation is that if we take a steel bar or a steel cube and we start hammering it, what will happen? It will deform for sure, but it will also get heated up, right, with the repeated blows. So there we are using the mechanical effect, mechanical field, and we get some thermal property, which is a raise in temperature. Right? So there also we see that these two fields are interacting with each other, and we can have coupling between, let's say, the magnetic properties and thermal properties. So you may have heard of a Curie temperature. So basically, if you take a magnetic material and you heat it, now at some temperature, which is called the Curie limit or Curie temperature, after that temperature, if we exceed that temperature, the material ceases to be magnetic, right? The material cannot be magnetic after that temperature. So again, we see that when we say that something is magnetic, we have to mention the temperature as well, or we have to have some background knowledge of what ambience we are talking about. So it's not an inherent property of that material to be magnetic. It's only under some favorable, let's say, some favorable conditions that some object can be magnetic. Or this could hold true of another property as well. For example, let's take the optical properties. So if you take, for example, uh, polyethylene, right? Polyethylene. If you take, let's see if I have something around. Yeah. So if you take sufficient layers of polyethylene and you stack them up, it will not be very transparent, right? So you can't see clearly through that. But if you take that bundle of polyethylene and then melt it, right, it becomes transparent. Okay, so that tells us, or even in glass blowing, we may have seen that as we heat the glass more and more, or as the glass is cooling, the shades of or the level of transparency, it also changes based on temperature. So clearly there we see that the optical properties of those materials, those are being affected or being altered by the thermal properties. And we could also have a link between, yeah, let's say, electrical properties and magnetic properties. Now these are, I mean, the famous example is the electromagnetic induction, the motors and generators and alternators, right? Those are all based on the interaction between these two fields, and how the that Faraday effect happens, right? You change the one of the fields and it gives rise to a corresponding other field. So that is the interaction between electrical and magnetic properties. And yeah, let's now see. Uh, so you may have heard of magnetostriction, right? So it happens in magnets that when they get magnetized, they get elongated or shortened along their axis of magnetization, right? And this effect is known as magnetostriction. And sometimes uh, so that there are two effects. One is the magnetostriction and another is the inverse of that. I'm forgetting the name. Magnetostriction. Let me see if I can quickly Google it. reverse of magnetostriction. Yeah, it's called the Villari effect. Okay, or it's also simply called the magnetoelastic effect. So basically, it's the inverse magnetostriction. Okay, it says that if you strain a material, if you apply strain on a material, it might develop some magnetization, and this will not happen in all materials, only selected materials, right? And similarly, you have the piezoelectricity in electrical, under electrical properties. You have piezoelectricity, and what would be the inverse? Electrostriction, or you can also call it piezomagnetism and magnetostriction, right? So that's the interaction between the electrical properties and mechanical properties, or the magnetic properties and mechanical properties. So we see all of these fields. These can be considered as fields now, that are applicable to, or that usually form the environment of a material. And when we talk of any particular property, it is also important that we have some notion of the range of other properties that under which we are defining that particular property. Okay, for example, when I usually say, let's take a bar of steel and apply some load, I am somewhere, I know that the thermal properties are around room temperature. The electric, there's no electric field or magnetic field in space, and I am doing it in, for example, say sunlight. Okay, so that kind of picture is already assumed, although it may not be explicitly stated. But we always need to have a notion of other range of other properties when we talk about any specific property. Okay, so that is the discussion on properties of different properties of materials and how they are related to each other. Now finally, I would like to expand a little bit on this mechanical property uh, aspect, and then yeah, so let's look a little bit deeper into the mechanical properties of solids. Okay, and I will talk about, so, mechanical properties of materials, and for simplicity I am going to assume that I am only talking about solids. Although it's interesting to note that the definition of solid and fluid, right, that comes from the mechanical property itself, that the whole definition is based on mechanical property, right? So how do we define a fluid? Some of you may know. So a fluid is a substance which does not sustain a shear stress, right? So shear stress, you may commonly know that if you take a, for example, if I have this book and if I strain it this way, if I push it on the top layer of this book, if I just push it like this, I drag it, you see that this edge does not remain vertical, right? Yeah, so this kind of a deformation is called a shear deformation. And now, so I am applying some non-zero shear force, right? And this material is able to resist that force by deforming itself. right? Because right now, see, even in this state, I am holding it like this. So there is some non-zero value of shear that is being applied to this material, and it deforms itself in a way to accommodate that shear, right? So this is true only of solids. A fluid cannot do it, right? So that is the definition of fluids, which comes from the mechanical property itself. So let's talk about the mechanical properties of solids. So how do we figure out the mechanical properties? Again, we have to interact with the mechanical load and that material. So let's, for example, consider a very simplistic situation. Although I must mention that a material, if we have a material, first of all, it can be of any shape, right? Uh, a most general shape would be, for example, say a potato shape, right? Let's say this is the material. And then when I say mechanical load, it can be distribution of loads can be in any given way. Okay, it can be very random. For example, there could be a large point load acting at one point, right? There could be smaller distributed force. Let's say somewhere I'm holding a material in my hand, right? And then let's say, for example, this kind of a situation, right? So I'm holding the material in my hand, so there's some distributive force from my hand, and then I am pushing on one point like this. So this could be a point load acting on that object. And then there could be body forces, right? For example, let's say gravity. Let's say there's gravity, and at every point of this body the gravity is acting downwards, right? So this force is acting everywhere in the body. Let's say this is body force, this is a point load, and this is a distributed load. So that could be the general way in which I load a body. And it's very so when I say mechanical properties of materials, so what am I talking about? Is there a specific shape or a specific load that I'm talking about? So generally in practice, what is done is uh, okay, okay. So one more point here. Okay, so first point is that loading can be shape of sample, shape of sample, and nature of loads. Can be arbitrary. Okay. And second point I want to make is, this is important. It's about, okay. So let me take a one square. Let's say this is a cardboard box. Okay. It's a, there are two cardboard boxes. One is a smaller one and one is a bigger one. And let's say there is some common surface. Let's say this is the surface of a table on which I am keeping them. Okay, and these are kept on the surface. Now I do something like this. Let's say I put a very high load of let's say 20, whatever, 20 kilonewton. Let's say I put a very large load here. Okay, and this cardboard box crushes. Okay, this gets crushed, while as the same load applied to this cardboard box, okay, same load applied to this cardboard box does not cause the failure of material. Let's say this cardboard box carries this load, and it's a very, you know, a very realistic situation. If there's a smaller cardboard box and you apply some force, large enough force, you can crush it. But if you apply the same force on a very big cardboard box, that cardboard box might carry that load without crushing, without getting failed, right? So what is now, since both of these boxes are made of cardboard, right? So are we really talking about a material property here? So if I say that, okay, this cardboard box got crushed in 20 kilonewtons, is that 20 kilonewton defining some property of the material? Because then the same material should fail irrespective of the size. The bigger cardboard box should fail as well. So this is the reason, like we don't whenever we talk about material properties, we don't talk about forces and displacements. Okay, what we talk about is stresses and strains. So stresses and strains are material descriptors, while as forces and displacements depend on material as well as geometry. Okay, so with this remark, whenever we talk about a material description, mechanical behavior description, we will always talk about the stress strain curve. Okay. Now, okay, so what the remark that we made is that this stress strain curve is indicative of the material behavior. Now the question is the behavior for all of the materials the same? Okay, so for example, let me draw a typical stress strain curve as uh, uh, as experienced while working with steel. Okay, a uniaxial stress strain curve for a steel specimen, and it looks something like this. Okay, while as for let's say, or let me draw them on a single plot to emphasize the point more. Okay, so I'll say that this is steel, and let me draw for copper. I hope it's different. Let me use a different color. Copper, right? And let me use again for, let's see, yeah, let me draw for steel, for glass, okay, for a ceramic. Okay, so this is ceramic. So the question is, why are these stress strain curves different, and what do they tell us about the material? Okay, there's a lot of, and what are the reasons that these behaviors are different, and what's the physics behind each of these behaviors, right? So that's a very long and elaborate discussion in itself, but so I'll just briefly mention some of the uh, observations that we can make from here. Okay, let's look at steel first. Okay, so for steel we observe that till this point, right, this point here, we see that the material behavior is almost linear. Okay, by linear I mean that it's a stress increases proportional to strain. You strain more, the stress also increases proportional, right? So, but after this point, something changes. Something happens at this point that immediately after this point, it is. Oh, I'm sorry. I messed these two up. It should be strain variable should be here. Stress variable should be here, right? So we see that after this value of strain, something happens to the material, that the stress drops first, and then there is some kind of a zigzag nature before and after that. So during this motion we see that strain increases while stress is almost constant. Okay, and then we see that there's an increase in the stress again. The stress goes high again as we change the strain, and it attains some maximum value, after which again the strain, with further strain, the stress starts to decrease. Ultimately at this point the material fractures. Okay, this cross represents that the material is fracturing. So again, if we now look at copper, we see that we see a similar, not as similar, but we see the trend. Like, we don't see this phenomena happening here, right? So we don't see a sharp drop in the in stress at some particular value of strain. Rather, we see a more or less a very a very monotonous behavior of stress with strain till the fracture point. But in case of a ceramic, right, for example glass, we see that there's very little strain that it can undergo, and the material fractures at a very little amount of strain, right? So this is so this behavior generally is for ductile materials. And the one in the red, where we don't have a lot of strain and the material fails before developing considerable strain, this is called brittle behavior. Okay, and we see that the stresses for this brittle materials, these are higher than those for ductile materials, right? And in and there's a very this zigzag motion, and why there's a sudden drop in this yield stress, right? So this point in this plot, it's called yield stress, and what happens here is called the yield stress phenomena, right? So but that's a very elaborate discussion. So the point is that the material behaviors are different, and based on the nature of stress strain curves, we can identify what kind of a material we are talking about. So given a stress strain curve, we have some idea about which class of materials we are dealing with. Okay, so that's the point I wanted to make. So I will stop here this lecture, and I will see you in the next TA lecture. If there are some questions, you can email them to me. My email address has been provided to you, uh, or you can also ask them in the next TA session, which will be live. And generally in live sessions, I will reserve some time for question answers and discussions. Uh, so yeah, see you in the next lecture. Thank you.